Assalamu alaikum. In this lecture, I will talk about the force due to external magnetic induction and a localized current distribution. The force is given by this expression. Now I'll assume that B sub R, the magnetic induction, is a slowly varying function, so we can expand this around some origin or a suitable origin. We use Taylor expansion. B of x is B of 0 plus R dot gradient B plus higher order terms. There is a vector sign here. Now this is the expression for the three-dimensional Taylor expansion. Now if we take one component B sub k, then this equation can be written in this form. So substitute in the force equation. This is the first term, which is where the argument of P is 0, and this is the second term. Now the first term, for localized distribution, we know that divergence J is equal 0, so integration over J dV prime gives us 0, so the first term is 0. Now we have to look at the second term. The second term is given by this expression. Now let's write one component in terms of Cartesian notations, which is the ith component, which is given by this. This is epsilon I j k, it's Levi-Zipf symbol. It's tensor of rank 3 times j sub j times p sub k. Now let us simplify this by writing this dot product as sum over Lx Ld sub x L. So we have to push this thing out, the integral, and we have to look for this. We already worked this in the previous lecture. We found that d3x prime dot xj is given by this expression, which is minus x prime cross c is the speed of light times the magnetic moment m. Here x prime can be any vector, it's an arbitrary vector. So this is the jth component now, which can be written in this form. Now if we look at this equation 3, 1 and equation number 2, this is equation 1, equation 2, equation number 3, we can replace x prime by negative mc, so we get this expression. Now back to the summation and get rid of the epsilon, we get the ith component of this vector, which means that f is nothing but m cross a gradient of a cross b. This is the force. Now this can be written in other form, which is gradient of m dot b minus m divergence b, but we know divergence b is 0. To get this form, again you can take the ith component of this. In this case you have a double cross product, you get double epsilon with they sharing one index, and then you can convert them into Kronecker delta. Once you do that, you get this expression directly. So the force is given by this now, a gradient of m dot b. If we look at this expression, we can deduce what's the potential energy, which is given by u minus m dot b. The torque, a similar work can be done for the torque, but here we have to do another cross product, which is r prime across j across b. Now b is written in terms of Taylor expansion at some origin. Now doing so, we finally get that the torque is m across b, the magnetic moment across the magnetic induction b. Now let's talk about the magnetostatics in the presence of matter. Here we have a specimen of magnetization M. It is known. We know that the number of dipoles dm is the magnetization times dV prime. Now we have to estimate the vector potential at some field point A corresponding to some element volume at R prime. So A is A sub J due to external field plus A due to the magnetization M of this material. This is for the external field expression, and this is for the expression for the vector potential due to the magnetization M, where I replaced dm by mdv prime. So we have m cross r minus r prime over r minus r prime cubed dv prime. This can be converted into this form using this identity, which also can be converted into this form using this identity. We get these two expressions for that. Now using this theorem, curl A dV is n cross A dA. We go from volume to surface integral. The first term can be written as this form and converted to surface integral, which is 0. For localized current, this thing must be vanished, where we assuming that m is a well-behaved function. If m is not a well-behaved function, we can convert this into surface integral, and then we can define what's called k sub b, which is in this case m across n. So we left now with two things, the first term, and this is the second term, the contribution of from the magnetization m. We have this is for A. Now we will call this as C curl M as G sum M capital magnetization current density vector. So A is given by this. It has two contributions, the external or the free current and the contribution from the magnetization, but we know that B equal curl A, so we have to take the curl of this thing, and using divergence A equals 0, this identity here, so we get this for curl B, which is minus Laplacian square of 1 over C times this thing, and we push delta inside, del square over r minus r prime, which is minus 4 by delta r minus r prime, and then evaluate the integration. We get 4 pi over c j plus j sub m. Now substitute for j sub m c curl m and take it to the other side. We find curl b minus 4 by m equal 4 by over c times j. We define the magnetic intensity h as b minus 4 by m. So we get curl h equal 4 by over c j. This is Ampere's law in matter. So we have two equations now. Divergence B is 0 and curl H equal 4 pi over C times J. And the connection between B and H is this relation through the magnetization M. In general, B is a function. This is a constitutive relation of H. It's not a linear relation, but some cases we can find that B is proportional to H by some constant. Let's call it mu. That's B equal to mu times H. This is true for isotropic diamagnetic and paramagnetic materials. For paramagnetic mu is positive, for diamagnetic mu is negative. So we can simplify here the above equation. That's it. See you on next lecture.